Good morning, ladies and gentlemen. My name is Pavel Kůs. My colleague's name is Alberto Gálvez. We are both students at Charles University and Institute of Physics of Czech Academy of Sciences in Prague. And we are super happy to be here and give a short talk about our project, which we started just recently. And as you can see, the project or this presentation is called Hunting Intermediate Mass Black Holes with Gravitational Waves and Neutrinos. So the overall goal of our project is to hunt intermediate mass black holes using tidal disruption events, which are events which produce gravitational waves and neutrinos.
You click on it.
Oh, perfect. Thank you. So this is the content of the presentation. I will start with what intermediate mass black hole is, what is the tidal disruption event, and how it can be used to be used as a probe to hunt intermediate mass black holes. What is the rates of these tidal disruption events, and then I will say something about the detection of gravitational waves, and then Alberto will start his part of presentation, and he will speak about neutrinos and future work and more advanced stuff. So for the beginning, what is intermediate mass black holes? You might know that there are three distinguished classes of black holes. They are distinguished by their masses. We distinguish them to stellar black holes, intermediate mass black holes, and supermassive black holes. While there is strong evidence for the existence of the first and the third class, there is still no clear evidence for the specific intermediate mass black hole. However, we expect them to be located at the center of dwarf galaxies and global clusters. So the purpose of our project is to actually look for the intermediate mass black holes in these dark galaxies and global clusters and contribute to the search of particular intermediate mass black holes. Until now, we have just candidates, but the evidence for the particular candidates are not that strong as for the other classes. So this is from first overall picture. So what is a tidal disruption event? Imagine that you have a star, and when it gets close to the black hole, it gets tidally disrupted. So you can see this light green star, and when it gets closer to the black hole, it gets squeezed, and when it's close enough, it gets completely disturbed by tidal forces and invertebrate and accretion disk, which can accelerate particles which can escape, and then after all, it produces neutrinos. Also, as in the scenario, what we assume, this star is on the quasi-circular orbits, which means that it produces gravitational waves which can be detected with the future experiment called LISA. So these are two observables what we take into account: gravitational wave emission, which comes from the quasi-circular motion, and neutrino emission, which comes from the formation of accretion disk. Okay, once we have the mechanism, we should know what is the rate of these events. So here, the most important sentence is the first one, and which is that if we assume that there are some models of dwarf galaxies, and they predict that if this dwarf galaxy has an intermediate mass black hole, it doesn't have to have it, but if in the case that it have it, it produces a tidal disruption event once per 1,000 years. And from all of these tidal disruption events, one comes from the tidal disruption event of the white dwarf in the scenario which I described before. There are also predictions for the tidal disruption events in global clusters. However, their contribution is negligible in comparison to the galaxies, so we can for now just focus on the galaxies. And if you want to see some nice formula, instead of what I just said, it is this formula, which means that the rate of tidal disruption events is proportional to the density of your galaxies at the time what we observe, and FD is ratio of white dwarf, of dwarf galaxies, which includes an intermediate mass black hole divided to all of them, and the smallest or expected, the minimum expected value is 0.2. As I said, there are two observables. One is gravitational wave emission from the quasi-circular motion, and this type of gravitational wave will be observed in the observation window of the future experiment called LISA, which will launch in 2037. And let me just say something about like its sensitivity curve and the noise over ratio, which we can signal over noise ratio, what we would be able to observe. Like this is the frequency what we will observe. It starts from 10 to the power minus hertz to 1 hertz. If we assume that white dwarf has mass around 0.7, which is the peak of the white on the distribution of white dwarfs, it always ended up by the disruption at this frequency 0.14, and this is basically describes that if we start to observe white dwarf here, it will take almost 1 million years to get it here, as it inspires on the circular orbits, and this orange point means that if we are 20 years to actually get here to the tidal disruption error. You can see that there are plenty of curves, and they also depend on the distance of the intermediate mass black hole to us. And for instance, this scenario corresponds to 100 megaparsecs. On the other hand, you can this absolute one, but not solid one, corresponds to 405 megaparsecs, and we can see that the characteristic strength, which is basically like the perturbation of the perturbation which is called the gravitational wave, but dimensionless, is smaller, which means that the signal over noise ratio will be also small. And yes, and we can compute the signal over noise ratio, and we computed from that. We expect that until this distance, it will be observable. This at least 3 or up to 20 years. This concerns the gravitational wave study, and now there is a neutrino part which will come by that.
Okay, so I will talk about the actual emission of neutrinos. And the idea here is that you have these TDEs happening in intermediate mass black holes. So you have a bunch of black holes, and they are happening these TDEs with some rate. So this will contribute to the diffuse neutrino background that we have of very high energy neutrinos that we talked about this morning. So it's important to know how many of these diffuse neutrinos are actually interesting for this study. So for this, you have to estimate what is the flux that you get at Earth. So with this, we use that formula. So this is the density of sources, which we consider constant. It's just the density of dwarf galaxies in our neighboring universe. And then this epsilon indicates how each source emits, right? Here is the rate of emission, which is just like how often do they emit, how often these TDEs happen. And this phi is the fluence. The fluence means, since these are transient events, so that means that they happen, right? And then they turn off, let's say. So that is the total amount of neutrinos that are emitted. Note that is proportional to the mass. Like in general, we expect that mass is the mass of the black hole, and we expect that black holes with higher mass will emit more neutrinos in this kind of TDEs. So with this, you can have a rough estimate of what the flux at Earth from these TDEs in intermediate mass black hole is. And then, of course, we compare with the flux that IceCube has already measured. So, well, one thing that I didn't mention, of course, this is a very rough calculation. We don't know exactly the details of how these fluxes, like how these tidal disruption emits neutrinos and what energy they peak and this kind of details. But we have rough estimates. And mostly the models that we have right now, they usually peak at around 10 to the 5 GeV. So around here, right? Yeah. And then you can compare what the preview integral gives you. You compare with this curve that I just measured, and you obtain this number here that is an important one. This shows that from between 4 to 21% of the, if our like a rough calculation again, but from 4 to 21% of the diffuse neutrino background should come from this kind of events. It's a big range because, as she explained before, we have this FD parameter, which pretty much means that we don't know how many dwarf galaxies actually have an intermediate black hole. So depending on that, you can vary. But even in the worst case scenario, 4% is something that for future experiments you could in principle work with, especially since for this to work, we have to wait for Lisa anyways. So and then I'll talk about this special case, the white dwarf case. Like how this started is because you have a white dwarf, and this will be tidally disrupted by intermediate mass black hole. This cannot happen with a supermassive black hole because the white dwarf is too compact, so it won't get tidally disrupted by it. It will get swallowed before it breaks down. So it has to be an intermediate mass black hole. And also it's compact enough that it will emit gravitational waves. So you have this very particular event that requires an intermediate mass black hole that will emit gravitational waves and neutrinos. So in principle, you could detect them both from the same point in the sky, right? Like this was the original idea, and this was like the ideal scenario, but it has a pretty big problem. And is that there are models of how this tidal disruption event happen. And usually like there is a expected time delay between the gravitational waves that happen because of the infalling of the white dwarf and the actual emission of the neutrinos. This time delay is of this order. Here, beta is the impact parameter, which means like how the white dwarf enters an orbit with the intermediate black hole is not the same if it enter like, let's say far away and it gets captured by the gravity of the black hole, or it goes straight into a black hole. Very different events. The eta is the efficiency, and then it has a very strong dependence on the mass of the black hole, which is the main point here, because if you have an intermediate mass black hole that is 1,000 times smaller than a normal black hole, then this time delay will be 1,000 times bigger. This means that you will have to wait. There's a number here, 30 years here. But again, it really depends on the mass of the black hole. But again, you will have to wait way too long. We don't want to detect gravitational waves and wait for 30 years for the neutrinos to be. So this is not really something that realistic, right? But it's not the end of the road, because there is another way of doing this. Since you don't have, like, you lose the possibility of doing a direct causal connection, right, in the sky, but you can still do a statistical analysis. How this works is that you just expect them all to come from TDEs from intermediate black hole, so they should follow the distribution of these black holes in the sky, right? Which is pretty much the distribution of dwarf galaxies. So if this is true, if they follow the same distribution, they should, when you study the angular cross correlation, you should find some evidence of this. How this works is that you have two independent maps, one of neutrinos and one of gravitational waves. And then you expand them into spherical harmonics and calculate the coefficient like this. This is the thing that you do for the CMB, for example. And then you do the cross correlation. So you cross correlate the one from the gravitational waves and the one from the neutrinos. And you get this CI that will have two contributions. The signal, that is what should be non-zero if this is the case. And noise, short noise, which is simply if you have two distribution of random points, it can just happen that two fall in the same place, right? So this is estimated by the short noise that depends like this. These are the common points between neutrinos and gravitational waves, and these are the points of neutrinos and gravitational waves. This is very useful because you see, like if you have either a lot of neutrinos or a lot of gravitational waves, you don't really need that many of the other messenger to be able to really reduce this noise and increase the chances of measuring the signal. But as the title says, this is future work because we have to work more on this yet. And to, like, the next objective is to estimate what kind of experiment we would need to be able to reliably measure this signal and be able to say that they do come, at least some of them, from the same sources. And that's all I have. Thank you for your attention.
Do we have questions?
Depending on the question.
Yeah, you mentioned that the expected time difference is 30 years between the gravitational waves and the neutrinos. Could you explain that again?
Yes. Well, first, I should say 30 years is a rough number if you put just some common. Like in the medium of black holes, they vary like 3 orders of magnitude of mass. So and you see this dependence. So of course, after 30 years, I think we calculated on the perfect event, like absolutely perfect, we only have 2 years of time delay, but that's like you cannot expect or hope for the perfect event. It's very unlikely, and the worst event will have hundreds of years.
And the gravitational wave arrives first.
Yes, like the point is that you have. Wait, I think I can explain with this thing. So you have a white dwarf that is captured, and then it slowly infalls because of the gravitational wave emission, right? So these are the gravitational waves you are measuring with LISA, not when it breaks. That one is not easy to measure for stars. It's not like with neutron stars, it's different. So you measure this gravitational wave, and then it breaks, and then you have to wait for the accretion disk to form, the particles to accelerate, and then you get the emission from neutrinos.
Right.
So that's where this key time delay comes from.
Okay, so the neutrino would match up with like an optical counterpart of the TDE, but not with this gravitational wave.
Yes,
Oh,
yes. Actually, it will probably come even after the like there are some studies that the optical counterpart will happen a few hundred days before the neutrino. But yeah, it will match up a lot better. The problem is with the optical counterpart, as I think we mentioned in some of the lectures, that these regions sometimes are very dense or obscure, so maybe the gamma rays cannot actually escape properly.
A very quick question. Yeah. So I was wondering if you can infer anything about primordial black holes, because they're we expect if they exist, they could fill in the gap of the intermediate mass black holes instead of the white dwarfs. If you don't see an angular correlation with white dwarfs, or you see an excess of events or something like that. Do you know anything about this?
Okay, and I mean, you mean like using primordial black holes instead of the white dwarf?
Yeah.
Yeah, the thing is, then you won't get any neutrinos, so there is not really a correlation.
Oh,
Yeah, like we count on the star to produce the neutrinos.
Okay.
Of course, in theory, you can measure those gravitational waves, for sure. And I mean, LISA should be able to measure them because there are similar ranges of frequencies. But you cannot do the same study, and then it's a matter of how precise, like how much angular resolution you can have just with the gravitational wave and all these. It's a completely different set of problems.
Okay.
Yeah.
Okay, let's thank Alberto and Pavel again.